Okay, so today we'll look at unit 9.4 and we'll look at delta G, changing free Gibbs energy, and we're going to relate that today to the equilibrium constant K. And this is also going to be with 9.5. So there is, I think we can just call this a plug and chug equation. Delta G equals negative R. Now this time the R is not the gas law constant because this is all about energy. So that constant is 8.314. Temperatures in Kelvin, still T, and then natural log of K. So if we know the K, we can figure out delta G. If we know the delta G, we can figure out K. But there's a little negative there, and basically what this is going to mean is that if you have a delta G that's positive, you'll have a K that's negative. If you have a delta G that's negative, you'll have a K that's positive. So let's kind of review a couple things also. Both these answers, or both these questions, deal with the same concept, and like always we have the answers already. So we have a chemical reaction, we have a delta H, we have a delta G. My first thought would be, before I even look at the question, it's going to be about this equation, but it turns out that that's not going to be the case with this one. But that would be my first thought, and that's a good first thought to have. But we already have, typically with that equation, we're solving for delta G, and we already have the delta G negative. That means it's thermodynamically favorable for this reaction to occur at 298 K. When you put equal volumes of N2 and H2 together, no formation of ammonia is observed. Even though delta G is negative, no reaction occurs. What would be your reasoning? And remember that collisions might be occurring, but they may not have sufficient energy to overcome the activation energy for this reaction to occur. It's very difficult to break the bond between two nitrogen atoms. That's a triple bond, very strong. So it does require a very high activation energy for this reaction to occur. Next one, no reaction occurs. If you spark it, then all of a sudden you get a very vigorous reaction. What would be that reasoning that the sparks required? Well, the same thing, large activation energy. Not quite as large as, I don't think it's as large as the formation of ammonia, but it does also require high activation energy. So actually there's a lot of thermodynamically favorable reactions that do require a lot of activation energy. Okay, so I said that there would be a relationship between delta G and the equilibrium constant. There we go. Here's our gas law constant. And by the way, not gas law constant, this is an energy constant, still the same unit R, or letter R, but this one has joules in it. But typically delta G is given in kilojoules. So if you would solve for delta G with this constant that has a joules, you'll get a very, very large number. People are always going to divide that by 1,000 to get it into a kilojoules answer. Okay, so keep that in mind. Also keep in mind that if you had a delta G and you were solving for K, your units aren't going to reconcile unless you get one to convert to the other. So take your kilojoules in the delta G and turn that into a joules. That would be what would be most convenient probably for most folks. And we already, there's a little review of K, what that stands for, what that means. Okay, so let's jump into one of these here. Calculate delta G. So again, this is more or less a plug and chug type of equation, or math I should say. and we have 8.314. We have a temperature of 298 K. We have a natural log of 1.6 times 10 to the negative 10th. When I do that math, I will get an answer of joules per mole, but that's not going to be something that I'm going to prefer because it's going to be so big of a number. So people are generally going to divide that by 1,000 to get your kilojoules. And when I did that math, I got an answer of 56. Okay, the negative that's in that exponent there and that negative out there, they'll cancel. When you do the natural log of something with the negative exponent, you'll get a negative answer, and then the negative in front of the R, those will cancel, so we'll get a positive value. So what does that mean? This reaction is not thermodynamically favorable. Design a method. So there's multiple ways to go about solving this. I'm usually interested in whatever way seems to be the least amount of work. But we'll talk about what would require lots of work. So you could go in the back of the book, and find delta S for this reaction using all the values in the back of the book that deal with the entropy of those four chemicals, get an answer, and then assemble it into this equation to solve for delta G. That, I guess you could say, is a two-part process, but what I would prefer to do is a one-step process, and I'm just going to go and solve for delta G using the sigma equation. And I'd go again in the back of the book and find the free Gibbs energy associated with those chemicals. This one and this one are elementals in their standard state, so they're going to have values of 0. So I only really have to go look at those. And so again, these ones are going to be kind of X'd out. Let me erase all that. But so the chlorine has a value of 0. Yes, there's 2 times that, but I don't really care about that. Then the H2O gas, yes, there's 2 of those, and that was negative 228.6 kilojoules per mole. And then all of my reactants, I need 4 times hydrochloric acid's value of negative 95.27, and then oxygen gas has a value of 0. And so when I do all that math, I get negative 76.12 kilojoules per mole. Just some relationships to what we might see in other science classes. So you could talk about ADP, ATP. This looks like to be a reaction that's not thermodynamically favorable. 31 kilojoules of energy stored. And then I think in biology class, at least when I learned it, they called it the currency of the cell. I don't know if they still do, but then you have 31 kilojoules per mole to do whatever work that needs to be done in the cell. The rest of these are all just practices here. We have a combustion reaction. So what do we know about the combustion reaction? Well, the delta G is already given. So if delta G is negative, that means it's supposed to occur. It's thermodynamically favorable. But it says here that it does not take place unless it's ignited. So we've already had 2 of these questions previously about the overcoming the activation energy, you have to break all those bonds, and that's going to take lots of energy. So unless you can overcome that activation energy, the reaction doesn't occur. Part 2. Predict the sign of delta S. Well, I think the easiest thing to do would be to just look at our gases. We have 12 gases going to 23 gases. That's becoming a lot more disorderly. So in my opinion, delta S is going to be significantly positive. And I think that will be enough justification. Let's double check. But let's, you know what, I don't think I have those answers. No, I don't have those answers, but take my word for it. Those are the answers for that one. Okay, we have another reaction here. We have some thermodynamic data, and let's take a second look at these because they're not in the same units, and that's typical. Delta H and delta G are typically in kilojoules, and S is in joules, because they want those answers, those numbers, to be convenient looking. They don't want them to be extremely small or extremely large. Let's see here. Calculate the value of K. Well, remember that if you have a delta G, you can figure out K. If you have a K, you can figure out delta G. So I guess I'll just put it here. Whoops. I have to put my negative in there. So delta G was, that's in kilojoules. Remember that R is in joules. So you have to get one of those units to match up with the other. So I'm going to change my delta G number and multiply 0.87 times 1,000. So that's going to give me now a unit that I like, joules. Negative 8.314. I'm going to run out of room here, so I'm not going to put my units, but these are in joules also. Temperature 298. And then I'm going to have to put this down here. Natural log of K. So we're going to solve for K. So you're going to have to remove that natural log from the K side, which is requiring you to use the anti-natural log. So on my calculator, it's right above natural log, which is the E to the X button. So that's fairly universal. It should be in that same location on your calculator that you're using. So when I run that math, and by the way, the delta G was a positive value, so I bet the K value is going to be negative. Does it come out to be negative? Actually, it's definitely going to be less than 1. I guess I shouldn't say negative, but less than 1. And do the math actually. Let's just look at our math. There we go. Whoops. 0.7, which is less than 1. Okay. Typically they will be negative, but they don't necessarily have to be negative if delta G is positive. It just has to be less than 1. Well, I guess it's never going to be, now I think about it, it can't really be, it's going to be something like, when I say less than a negative, I mean, I guess, like the exponent there, sorry. Oh, let's go part B. If the partial pressures were initially at 1, will the partial pressure of N2O3 at equilibrium be equal to 1? Well, I think we've done enough IC tables to know that that's virtually never the case. That would mean that it ran to completion, and these aren't running to completion, these are equilibrium. But also we can talk in terms of K is less than 1. That means you have just a little bit of forward reaction and a tremendous amount of backwards reaction. So you're going to have something much less than 1 atmosphere. Let's double check our answers here. No, the pressure will not equal 1. I guess I kind of answered them both ways, but you don't need to do it both ways, talking about both of these. So I said it doesn't go to completion, and then also because the K is small, you're going to have a lot of reactants and not many products at the end of the day. Part C. Student hypothesizes that increasing the temperature will increase the amount of N2O3. What will happen there? Well, I guess there's a lot of ways you can kind of talk about that. This is the way I'm going to talk about it. I don't know if they're going to decide to use that same method that I'm using. So we already know that delta G is positive, right? Well, let's back up a second. It was positive at 298. The student is saying that if you increase the temperature, you can make this reaction occur. So they want this to become negative. The delta G is still going to be negative. And we have a negative here for delta S. Okay, so if you did increase the temperature, that's actually going to make this part become a larger digit, and it's a negative times a negative. So actually that's going to have the reverse effect of what we want to happen. That's going to make the delta G become more positive, not more negative. So extra temperature is going to have the opposite effect. So I do not agree with that student. But let's check out what these guys say. They did say disagree. They say it's exothermic. So they came to that conclusion by looking at the thermodynamic data there. Increase the temperature. So they mention about the Le Chatelier's principle. So that would be fine too. Oops. Okay, so we got part C done. I think we have one more question here. And this question is kind of more all-encompassing. It's not all about thermochemistry. Explain why the diagram on the left is a better representation for the bonding, and use formal charge. So formal charge is something we haven't done for a while, but we're never going to worry about the hydrogens because they're bonding always the exact same way with everything. So we're just going to be concentrated on those 3 atoms. And you have to do each one individually, and we're looking for the answer that has the most zeros. Save me some time if actually they didn't break it down, so maybe I'll break down the C here for that one. And so you do valence electrons minus the unshared. There are no lone dots with carbon, and then you do half of the shared. So basically if you just look at the lines, so we have a total of 4 lines. That gives me an answer of 0. Let's do the nitrogen. Nitrogen has 5 valence electrons, no lone electrons, and it looks like it has 4 lines, which that's going to be half. If you just count the lines, that gives you half of the bonded electrons. That gives you a +1. +1s are not ideal. We would like zeros. Oxygen, 6 valence electrons, 6 unshared, and then we have 1 that's shared, or half of the 2 that are shared is 1. So that gives you a -1. So not ideal, but it might be better than what we're going to get over here. So carbon, 4 valence electrons, 2 unshared, and 3, half of the 6 that are shared is 3. That gives you a -1. Nitrogen, 5 minus 0 minus 4 gives you a +1. Oxygen, 6 minus 4 minus 2 is 0. This is a difficult one here. I don't know if you're going to get this kind of question very often on the AP tests. But what should happen, we would love, if you have to break a tie, we would love carbon to be 0. Carbon is not very electronegative, and it should be 0 would be awesome. You would love that the most electronegative atoms are negative. Oxygen is our most electronegative atom. It's a negative. I think this one's very difficult. This one's a little more in depth than I think most of these are going to be. Yeah, so it mentions some of the items that I had already talked about there. But usually it'll be clear cut that one of these formal charge answers will have almost all zeros, if not all zeros. Not the case with this one. Part B, use the Lewis dot diagrams that are shown there to figure out the bond enthalpies and determine the value of delta H for the reaction. So the reaction is left to right there. So you got to go find all those bonds, and these are all needed to be broken. So they have to be absorbed energy, so they have to be positive numbers. And then all these bonds are formed, so when you get all those values, those have to be negative. And I think they probably have an answer for this one. They do. Negative 246 kilojoules per mole. So overall, this reaction is exothermic. Part C, student claims that delta S for the reaction is very close to 0. Explain why the student's claim is accurate. Oops. So let's go back here and let's erase some of these items. Okay, so both of these have the exact same amount of atoms. They are both gases. There's very little differences as far as disorder with these two compounds. So I think something to that effect would tell you that this delta S is going to be very, very insignificant. Yeah, so just it's a rearrangement of the atoms, no changes in phases, no changes in the number of molecules, so forth. So that works. And then our last part, part D, which species is present in higher concentration at equilibrium? Justify your answer in terms of thermodynamic favorability and the equilibrium constant. So we have some things we can talk about here. Let's go delta G equals delta H minus T delta S. So if we know that it's thermodynamically favorable, that's going to mean we have more of this. if it's not thermodynamically favorable, we have more of this. That's the idea. So we had a delta H that we were just given, well, not given, we just solved for, negative 246. We have a temperature. Do we have a temperature? We are not given a temperature. We are, 298. And then to remember that delta S was told to us, or we had to come up with a reasoning why it was close to 0. So when you do all that, you're just going to get that negative value for delta G, which means it's going to have lots of left to right. You're going to make lots of product. So I think that is how we're going to get to that answer. I don't know if they used the same reasoning. They did use some of the same reason as I used. Okay. And that might be, I think that's it.